Hello and welcome to In Control, the first podcast on control theory. Here we discuss the science of feedback, decision-making, artificial intelligence, and much more. I'm your host, Alberto Paduan, live from a recording studio in Zurich. Big thanks to our sponsors, the National Center of Competence in Research of Dependable Ubiquitous Automation, International Federation of Automatic Control, and the IEEE Control Systems Society. We are honored to have as our guest today Bart De Moor, professor in the Department of Electrical Engineering at KU Leuven. Welcome to the show, Bart.
Thank you very much. Thanks for having me.
So, Bart, as I mentioned, it's an honor and pleasure to have you here. Your work speaks for itself. I hope we'll give it the spotlight it deserves today. I'd like to perhaps start this episode by mentioning that one thing that is common at the date of recording is that both football teams of our national teams are out of the Euro Cup. And another thing that possibly is common among us is classical studies and the study of music. Mm-hmm. I thought about starting from there, basically thinking about how studying those subjects before your higher education affected you in the person that you became, and how did you stumble on control theory?
Yes, so if I go back to my, let's say, secondary school education, I did a discipline that is called Latin mathematics. So it's really a classical study, in which case we had like 6 hours of Latin per week for 6 years. We had 8 hours of mathematics per week, also for 6 years. And apart from that, we had all the classical courses of history, geography, biology, you name it, but also languages. So we had a lot of English. French is actually my second language. English is my third language. And unfortunately, I did not have any German, but instead I had 2 hours of philosophy a week. And the teacher of philosophy always said that we didn't have to bother about the lack of German because philosophy encompasses German. And so basically I don't know any German, but I know some philosophy. So that's thanks to my classical education. And the system in Belgium is that when you want to become an engineer, in my case, an electrical engineer, then there is an entrance examination, which is pretty hard. So it's quite competitive. And so I did that when I was 18. So after my secondary school at the University of Leuven. And I was very happy to be admitted. So basically this classical education leads to, if you really want to become an engineer, then it leads to the entrance examination of engineering. We also have other entrance examinations, like in medicine. It's also a mandatory entrance examination, but I did the one for engineering.
And then, as you say, you studied electrical engineering, I believe at KU Leuven.
Yes.
And I was wondering what has drawn you to control theory.
Yeah, so the system at that time was that you had first 2 years of, let's say, general education in mathematics and physics. So that had to be followed by all engineers over all disciplines. And then after the second year, you had to choose. And at that time, there were still fewer departments than we have now. So at that time, I'm speaking about 40 years ago, you had the classical ones like electrical engineering, mechanical engineering, civil engineering, computer science. Computer science was relatively new at that moment, but I worked by elimination. So I was not interested in chemistry, nor in material science and so on. And I had 3 options: computer science, mechanical engineering, and electrical engineering. But this is 40 years ago. So it was being the time where the personal computers were launched. I mean, Microsoft, where also the importance of the chips industry became apparent. You had Intel and so on and so forth. And so computer science I did not do because I did not want to become a coding nerd. And I was interested in mathematics. And when I compared the courses, I saw that electrical engineering And of course, especially control engineering, because that is deeply rooted in, on the one hand, mathematics, but also on the other hand, in electrical engineering. Because if you think about the classics, electrical circuits, if you think about Bode, if you think about Shannon, Nyquist, and so on, in one way or another, they were all electrical engineers or very close to electrical engineering. And so I think that was the main motivation for me, first of all, to choose for electrical engineering. And then in a second phase, we had to choose in the electrical engineering discipline. So I think there were 5 or 6 possible options. You had telecommunications, you had nanotechnology, you had image processing, and so on. But then I thought that control engineering was very close to my heart because, if you looked at the courses, it was all about applied mathematics. And I've always been hesitating between mathematics and engineering. And so, but of course, my father was also an engineer, and mathematics at that time, and maybe it has not changed too much now, the future for a mathematician is not as bright, not as broad as for an electrical engineer, of course. And so that's why I ended up in electrical engineering. Yeah. But I've never really done the profession of an electrical engineer. So I'm trained as an electrical engineer. I know a lot about it, but I've never done the real job of an electrical engineer. Yeah.
It resonates very much also with the path that I've taken so far. So I can definitely identify in the words that you've just said. Okay, so just to situate also historically where we are in time, we're talking about 1983, and that's the start of your PhD, if I'm correct, with Jos van der Walle. I apologize for the pronunciation. I'm not sure how to best pronounce Flemish names. So the title of your PhD thesis is Mathematical Concepts and Techniques for Modeling of Static and Dynamic Systems. I personally enjoyed very much reading this thesis. It's 341 pages, filled with lots of interesting stuff, from non-negative linear algebra, linear complementarity problems, neural networks, numerical linear algebra, identification, system theory, realization theory in particular, and also what forms the basis today of subspace identification. I have an impromptu question related to the PhD thesis, and maybe we can move on to the contents. Who did the illustrations?
I think I collected them while I was doing my PhD. You have to realize at that time, we did not have internet. So there was no Google and no nothing. There was LaTeX. I used LaTeX. But to give you an example, we could not include the figures in LaTeX. We had to leave open space and then to paste them into the things. And basically, because there was no internet, I spent hours and hours, if not days and weeks, in the library of mathematics, where they had all the journals and where there had a lot of books and so on. And that was a bit problematic because, you're working on your PhD, you try to focus. But of course, if you spend your days in mathematics, there are so many things that you can learn and that you can. And so from the beginning, I had a reflex. We had a copy machine in that library. And whenever I saw some interesting picture or something like that, I just copied it. And so I didn't bother about copyright and so on and so forth. That was not a hot issue at that time. And I guess I should look it up again. But some of the illustrations in the PhD are copies of existing books and so on and so forth. And I think, I made a couple of figures myself also. But that was, at that time, that was really difficult because there was the first versions of MATLAB. But then to go from the MATLAB figure that you saw on your screen to have that into the text at that time, there were no, that was a very complicated procedure, working with PS files and things like that. It was very, very technical. And of course, I had a couple of PhD students that knew their way around that really could help me in doing all the technicities and solving the technicalities in order to. So it's nothing comparable with what we have now, where with one push on the bottom of your keyboard, you can include a figure wherever you want. It was really very, very painful. Yeah.
I'm very struck by, some of the statements below certain figures, one of which I noted down. I think it's on page 183. It says just below the figure, science models are rather a simulation of human consciousness than the reality of the universe.
Yeah.
And generally, I mean, it's really fun to read this thesis. Another quote that I noted down, page 83, just after finishing the chapter on generalized linear complementarity problems, you write, as a matter of fact, many more results have been obtained since this chapter has received its final shape. Therefore, let's conclude this chapter with turning a blind eye to Pierre de Fermat and the mystery surrounding his famous last theorem. This thesis is too small to contain them all.
At that time, Fermat's last theorem was not yet proved. Of course, it was proved 20 years ago by Andrew Wiles, but at that time it was not yet proved. So it was a little joke I could afford myself in the thesis.
What I really found fascinating, personally at least, is the chapter 5 and 6, where you really feel the influence of Jan Willems. You actually start, I think, chapter 5, the incipit of chapter 5 as a quote from Jan Willems, where you write, models are a matter of inspiration, not deduction. And there is a whole chapter 6, dedicated to what you call the uncertainty principle of mathematical modeling, where basically you have 3 important points that I may summarize very bluntly with identification is a matter of definition, uncertain data imply uncertain models, and noise is defined once the model is defined. I really recommend every student listening to this podcast to read that chapter. I think it's very profound. I'm just curious about your thought process. How did that originate?
Yeah, I think that's an you give several ingredients that I can talk about. Maybe first of my PhD, as you said, it has 3 big parts, if you want. The first part is all about solving sets of linear equations, but with non-negativity constraints, which is kind of an interesting mathematical problem, and which I applied later on, even after the PhD thesis, to many other fields. So one of the fields was nonlinear, piecewise linear electrical circuits. I mean, you can phrase that as a modeling problem where you have non-negativity constraints on some variables in a set of linear equations. A second one is called complementarity problems. You referred to that. I'm not going to explain what that is, but if you study a course in optimization, you know about the Karushka-Tucker conditions, and some of these conditions are complementarity conditions. I mean, I'm not going to elaborate on that. And a third part led to results by some of my later PhD students who all became a professor in what is called the max algebra. And the max algebra is a very funny algebra where you replace the product of numbers by the sum of numbers, and the sum of numbers is replaced by the max algebra. And you can then write down, for instance, state space models by replacing products by sum and sums by maxes. And that, for instance, that kind of algebra is used in discrete event systems. And there we could generalize in that max algebra things like the singular value decomposition and like realization theory, but then in that new algebra, so completely changing the conventional operations, arithmetic operations you have. The second part of my thesis is indeed, and I will comment on that, on what you could call the uncertainty principle. And the third part, and I'm sure we will come back to that later, is about basically the beginnings of subspace identification. And there, indeed, I was in both chapters, I was inspired a lot by Jan Willems, who is, in your life, you only have a couple of people that you can call mentors. And mentors, I mean that people that guide you and that later on become close friends of yours. And Jan Willems was definitely one of these figures. You have to know he is Belgian because he has a twin brother who later on became the rector of the University of Ghent. So in Flanders, you have 5 universities. And the twin brother of Jan Willems was the rector of Ghent. So I knew the Willems, the both of them, quite well. And Willems was a professor in Groningen, but at one of the first conferences I went to, I talked to Jan Willems because he was Belgian and I knew about him. I knew his name because he has this big track record already in the 80s. He had done a PhD at MIT and so on. And via Jan Willems, I got into touch with Kalman. And Kalman was not working on the Kalman filter anymore. I mean, he was, of course, famous for his contributions to state space theory and to the filtering problem and to LQR and so on, LQG, Riccati equations. I mean, Kalman had a big reputation when I made my PhD. Actually, in some of the control courses we had, or in all the control courses, at that time, there was not yet a lot about optimal control, because if you think about it, at that time, it was only like 10 years old. And so it had not yet pervaded in the, of course, now it's in all the courses that you can imagine. But at that time, we really had to study it ourselves and to read about it in the library and so on. But the problem that Kalman was working on, I found it an interesting mathematical problem, and it seems quite easy at first sight, but it is not. And so I can easily phrase the problem that as follows. I give you a square matrix. It's symmetric and it's positive definite. So it's a positive definite symmetric matrix. And now you can only modify the diagonal elements. So you can subtract positive numbers from the diagonal, different positive numbers, in such a way that you keep the difference non-negative definite, so it has to semi-definite positive, and you try to minimize the rank. So you have a symmetric positive definite matrix. You are only allowed to play around with the diagonal elements. You try to minimize the rank, but the result should be non-negative definite, okay? And I was looking at the problem, and suddenly I realized that I could link that up to the first part of my thesis, which is about this solving sets of linear equations with non-negativity constraints. I cannot explain that now in detail. You have to read my PhD thesis. But the big thing that Kalman said was that typically in statistics and also in the Kalman filter and so on, you think about solving an estimation problem or an identification problem in least squares, and that leads to one solution. I mean, under certain conditions, you only have one solution. And of course, you can talk about a distribution of the uncertainty around that one solution if you have certain a priori assumptions about the distribution of the noise and so on. But Kalman derived another framework, and it was not due to him. It was an old problem that was posed by a certain econometrician called Frisch. It's called the Frisch scheme. And so it's that mathematical problem. And there you can show that if you have a very strict definition of the noise, and that's what you were citing, noise is everything that is not compatible with a model. And so basically, when you talk about linear models, so you talk about least squares, orthogonality is very important. And so you have an interplay between a model that you choose and all the data that are not compliant with the model, so that cannot be explained by the model. Basically, you have to modify these data in such a way that the modified data are compatible with the model class you have chosen. I mean, it's a bit of philosophy, and of course, engineers, they say, okay, with the data we have, we cannot solve the problem because the data are not compatible with the model. So let's change the model. And you can call that noise, if you ask me. We call it misfit. Jan Willems calls it misfit, least squares misfit, for instance. And so that problem was around in the 80s. And with the results of the first part of my thesis, I could make a lot of progress in that problem. So I could, for instance, derive the minimal rank achievable and so on and so forth. But in my PhD thesis, I was not able to fully solve the problem. I mean, I was missing certain pieces, and I formulated at a certain moment a conjecture. And later on, like 10 years later, that conjecture was refuted by Anderson and by Deisler. You know, Brian Anderson, who is also a very famous system theory person. And I was very proud. I mean, at the one hand, I was disappointed, but the title of the paper was something like De Moor's Conjecture Refuted. So it's a kind of negative result. But at one hand, I was disappointed. On the other hand, I was kind of happy that they called it De Moor's Conjecture. And so it's a very geometrical thing. So there is no statistics involved. Basically, what you describe is that a whole collection of models, and the least squares models, you could think of several least squares models. They are in that set of solutions under all these conditions that I cannot go into detail, but it's a completely deterministic theory that describes the uncertainty on the optimal estimates you achieve. And so it's a non-statistical theory. And Willems liked that very much because, of course, we have to be careful in what we say, but if you use statistics, you always use a priori assumptions, and these a priori assumptions cannot be verified on the real data. If you assume that the uncertainty on your data is Gaussian, well, I mean, that's an assumption, right? How can you possibly test whether that's the right distribution? So once you make an a priori assumption about distributions, you can do a lot of mathematics, and that is what statistics is about. But we tried to come up with a theory which led to nice mathematics, and unconventional mathematics, I must say, in which you did not need the real statistical assumptions. I mean, it's a certain philosophical approach in which you say that everything that is not compatible with the model, I call it noise. And based on that principle, you can read those 2 chapters in my thesis.
This is wonderful. I find the subject extremely fascinating on my end. I'm tempted to cite everything that I read in that chapter because the whole discussion links many important viewpoints, I think.
One thing I want to add is that the Frisch scheme and everything Kalman, there were some gossips that Kalman was changing topics because, and this was considered to be a kind of econometric topic, because the gossip was that he wanted to get the Nobel Prize for economics. And of course, I cannot verify that. It was just a rumor, a gossip. The second thing I want to add is that the Frisch scheme, as it's called, basically did not survive because the minimum rank solution that we found has a kind of non-generic lower bound. So let me give an example. If I start from that data matrix, that positive definite symmetric matrix, and it's a full rank to start with, and so there is a kind of lower bound that you can achieve because of the mathematics. It has to do with genericity and so on and so forth. Now, if we start from a matrix, an exact data matrix that is rank 1, and then you add a little bit of noise to everything, the resulting covariance matrix will be positive definite. It will be a full rank. But that lower bound, I think it's called the Lederman lower bound, makes that you can never find back the rank 1 solution. So for instance, if you have 10 variables, then the lower bound is maybe like minimum rank 5. I'm not sure, but suppose it's rank 5, but it's not rank 1. So it means that when you look at the singular values of that data matrix, you will clearly see that there is one dominant singular value and there are 9 small ones. But that is not revealed by the Frisch scheme. The Frisch scheme will say that the minimum rank achievable is 5. So it means that really very small perturbations make it very impracticable to use with real data. So there's this kind of thought experiment that kind of completely invalidated the Frisch scheme. So that's why it kind of died after 15 or 20 years. There were people like Professor Guidorzi in Bologna, with some of his students that also worked on it. But I think the last publications appeared about it, I think like 20 years ago. So it had a very short life cycle, so to say, because of this kind of non-generic behavior. I mean, it's when you work with real data, it can give you really wrong impressions about what the data really are.
This is extremely fascinating. Again, I encourage all the listeners to read up that chapter. It inspired me a lot, first of all, in following up on the relevant citations, some of the work by Willems, which I want to ask you about in a second, and also of Kalman, as you mentioned. In fact, you finished your PhD thesis in 1988. 1986 is the year instead where the famous three-part paper by Willems on From Time Series to Linear System actually is published on Automatica. And I was wondering, how did that influence, your research in this chapter, but also in the next one on the genesis, if you wish, of subspace identification?
Yeah, I think those 3 papers of Jan Willems, and I can also advise everybody working in system identification to read those papers because they are important. They had a big impact on me. Basically, the first paper comes with a kind of conceptualization of system identification, and there Jan comes with relatively new notions like behavior. And so if you have the data set, he calls that the behavior. And a model is a good model when it can kind of reproduce the behavior and it's close to the behavior and so on and so forth. He comes with all kinds of new names like kernel models and image models and so on. I mean, it's a kind of formalization. And I think it was very important because I was trained in system identification with the classic books by Leonard Jung. And Leonard, by the way, is also one of my mentors. So what I'm going to say is not meant to be insulting in one way or another. But if you read the book by Leonard, it's really a book about applying optimization to data to system identification. But in a certain sense, it's heuristic and it misses a little bit the rigor by which you can I mean, there's a lot of hidden knowledge in that book, there's a lot of statistics and so on and so forth, which makes it kind of hard to really understand. You can argue that what Jan Willems did was the opposite, because he formalized the whole thing maybe a little bit too much because the language of behavior is kind of abstract when you see it for the first time. But one of the results, and I think it's in the second paper, I'm not sure anymore, but was a very interesting linear algebra result, which says the following. I give you input and output data, and now already make a sin against behavior because Jan refused to recognize that there are inputs and outputs to a system. But let's not go into that because I had a lot of discussions with Jan. I said, look, I mean, I'm an engineer, and for sure we know for certain systems what inputs and outputs are. I mean, but that's a kind of very philosophical discussion. But if you have inputs and outputs, and suppose they are what today we would call model compliant. So they are generated by a linear time invariant system, finite dimension, and so on and so forth. And you throw those data in some Hankel matrices. So the Hankel matrix pops up there. And in that sense, it's a kind of generalization of the Kalman realization theory, because Kalman started with Hankel matrices with Markov parameters or impulse response samples. So we kind of generalize this to input-output data. And then the intriguing result by Jan Willems is that you can make a big Hankel matrix, you can chunk it into two parts, and the upper part you call the past data, it's just a name, and the lower part you call the future data. So you have these two huge row spaces with data, past row space, future row space. And then the result is intriguing because it says that there is a non-trivial intersection between those two row spaces, and that generates a third row space, which is the intersection of the two row spaces, and that row space is the state sequence row space. So basically it shows that from input-output data, you can find the states of a system without having the model. I did not mention the model. The only thing I said is that the underlying assumption is that the data are generated by a model, by a linear time invariant model. But by just using linear algebra and by making these Hankel matrices, a past Hankel matrix, a future Hankel matrix, calculating an intersection of two row spaces is a linear algebra problem. It's just solving a set of linear equations. But the conceptual result is that you can deduce from input-output data without having the model, you can deduce the state sequence. And that is a kind of change of paradigm when you compare it to Kalman. So what Kalman said is, first you need to have the state space model. And once you have the state space model, then you can use, for instance, a Kalman filter or a Leuvenberger filter if it's more deterministic, and then estimate the state. So first you obtain the state space model, and then you estimate the state. We reversed the order and we said, no, you can first estimate the state. And if you have the inputs, the state, and the outputs, then it's easy, relatively easy to find the state space model. So it's a kind of change of paradigm in system identification. Now, Jan Willems did that for deterministic data, so noiseless data, so to say. And I was at first a bit disappointed because in one of the last chapters of my thesis, I derived the same result. I had the same result. And of course, Jan scooped me in publishing it. And he called the dimension of the state space, so the dimension of that intersection, he called it the relative row rank. But I had found a much older reference for linear algebra, not in terms of linear systems, but it's called Grassmann's dimension theorem, which basically says that the dimension of an intersection of two sets is the sum of the dimensions of the two sets minus the dimension of the union. And basically, I used that Grassmann's theorem. It's a special case of what is called the inclusion-exclusion principle, but that would lead us too far. But in any case, it's just a linear algebra operation by which you can estimate from input and output data, you can estimate a state. And that's for deterministic systems. And then there was also in the 80s a famous paper by Akaike, who did it for stochastic systems. So when you don't have a deterministic input, but you have white noise driving a dynamical system. And there you can also estimate the state, but it's not an intersection of a future and a past Hankel matrix. It are what is called the canonical correlations, the principal angles between spaces generated by future and past. And so I started thinking at that moment, we have the deterministic case. I mean, that's Jan Willems, that's also in my PhD. I calculated the stochastic case. What if you have what we called the combined case? What is the combined case? It's a normal state space model in which you have both deterministic inputs and stochastic inputs. So basically the model that is being used in a Kalman filter. And so the question then is, when I only give you the deterministic inputs, when I give you the deterministic outputs, can I estimate the state sequence as it would be delivered by a Kalman filter without having the model? Because remember, we are changing the paradigm. We are first going to estimate the state sequence, and then only in a second phase, the state space model. And so that's basically one of my first PhD students, Peter van Overschie, who worked that out in his PhD. And that led then later on to our subspace identification book. And so your question about Jan Willems is very relevant to me because he was one source of inspiration, also for my current work now. You know, almost every day I think about Jan Willems in the sense that what would he say about this statement or that? Because Jan was a very critical but very intellectual. I mean, I love to have discussions with Jan, not only, by the way, about science and system identification, but about everything, about politics, about life, and so on and so forth. And so Jan was definitely an important source of inspiration for subspace identification. But in his 3 papers that you started with, he only solved part of the problems that later on we solved. Akaike was definitely another source of inspiration. And basically, Jan had some problems with Akaike too, because Jan, deep down there, did not really like statistics. And of course, Akaike is a really stochastic approach, and there have been lots of people working on stochastic system theory, but still, you always need a priori assumptions that you cannot verify. And so that made Jan and also me a little bit uncomfortable. By the way, you see it a lot in data science these days, where they use deep learning and so on. Actually, they ignore everything that is known about statistics. They don't care. They don't care about statistics at all. And so yeah, the position of statistics is a little bit. I mean, you can discuss about it. Let me phrase it like that. I mean, it's a nice scientific discussion. Why do we need statistics? But I'm not going to provoke too much. So, yeah.
I'm sure that this will spark a lot of discussion also as a follow-up of this episode.
Yeah, exactly.
It's a question that I resonate very much with and that I personally think about a lot. Well, just one comment, and then I'll ask you one provocative question, and then maybe we can also move on, because this is just the inception of your research journey.
Yeah.
The comment I want to make is that, of course, the book that we mentioned before is Subspace Identification for Linear Systems, Theory, Implementation, Applications. It's a book that you published together with Peter van Overske in 1995. There will be a link in the description. And obviously, that essentially works out subspace identification theory, both in deterministic and then in the stochastic case, as you say. In the same years, you also published this paper on M4SEED, subspace identification algorithms for the identification of combined deterministic stochastic systems. There will be also a link to that. The provocative question I want to ask you before we move on to your postdoc years is related to behavioral stochastic theory. I think it's still an open question what a behavioral stochastic system is. I had similar discussions with people in system identification lately. I wonder what's your opinion on the subject?
Yeah, I think we can come back to that later, but I have an answer to that. It's basically on this interplay between, so Jan Willems at a certain moment said that in many cases for engineers, models are a matter of inspiration and not of deduction. That's not completely correct, of course, because if you think about physics, there it might also be deduction, because you have a lot of experiments and you try to figure out what the laws are. But at a certain moment deep down there, it's maybe always an act of inspiration. At a certain moment you say, let's try it for this type of model. And then I like the idea of what is then noise or uncertainties is everything that cannot be explained by the model. So that's a non-statistical, non-stochastic definition of noise, if you want. And this question about behavior and stochastics, I had quite a lot of discussions with Jan Willems the last 10 years of his life, because, he was a professor in Leuven, because he retired in Groningen. And the law in the Netherlands was that when you retire early, you could keep 80% of your salary for the remainder of the years. And you could move to any university you want. And when Jan informed me about his situation, I said, yeah, why don't you come to Leuven? So he spent the last 10 years of his life in Leuven, and we had a weekly lunch and so on. And that, Alberto, was one of the reoccurring questions, because I kind of challenged him. I said, look, if I see your papers in Automatica, also the third paper there, the third classic paper, which he did with Christian Heij, is a kind of deterministic procedure. It's SVD based and so on. But there is a problem. It does not have any optimality problems. I mean, they use SVD, but you cannot qualify or quantify the resulting model that it would be optimal in one way or another. I mean, that's one of the issues there. And of course, with Subspace and the stochastic versions of it in our mind, I kept on provoking him for what is stochastic. And I think he was thinking about it, but it never materialized. Because, of course, when you go back to the foundations of statistics, that's a very difficult thing. I mean, are you going to adhere to a frequentist approach? Are you going to use Bayesian? You have also quite some recent books about the foundations of probability theory and so on. So how far do you go? I mean, what are the principles that you are going to adhere to when you're talking about behavior and stochastics? So I'm afraid to say that he never managed to come up with this kind of lacking part of behavior theory. Yeah. So you could say it's still open. Yeah, that's right. Yeah. And I even don't know whether there are currently people working on it. I think you should have to ask, you would have to ask the former students of Jan Willems, like Paula Rocha, for instance. Maybe she knows the current state. I'm sure there must be people that have been working on it, but I did not follow those developments. Yeah.
There's one recent attempt in the literature that I'm aware of by Giacomo Baggio and Rodolphe Sepulcre. It's a short conference paper, but maybe we can defer and actually try to do justice to the rest of the body of work you've done.
I should ask Rodolphe, because he is, since 1 year, he is a direct colleague of mine. So he also joined our department.
I'm curious about what he will answer to that. But anyways, so it's 1988, you finish your PhD, as you say, and you move to Stanford to work with two other giants, I would say, one in systems and control and the other one in numerical linear algebra, namely Thomas Kailath and Jean Golub. I'm wondering, how were your interactions with those giants there?
Yeah. I think this was still in the 80s. So when I try to explain this to my PhD students, you have to realize that, for instance, the funding to go abroad was almost inexistent. So at a certain moment, I got a grant of $3,000 from NATO. I applied and I got it. And so that's the amount of money we left. I had a loan from my father, I think, of another $3,000. And that's me and my wife, we left for Stanford. And I had met Golub and Kailath at a conference in Barcelona. And I knew of them, of course, because Kailath had written a very famous book on linear systems. I mean, that was a bit of our Bible of linear systems. And then Golub was, of course, already very famous for singular value decomposition, also one of the fathers of MATLAB, and a bit Cleve Moller, and so on. And so I approached them in Barcelona, and I said, look, I would really like to come to Stanford. I mentioned some names that they knew. Joost van der Wallen, my promoter, they know. They also knew Paul van Doren, who was a very famous numerical linear algebra person who had also been in Stanford and so on. And so I did a little pitch saying that, look, I have like 1/3 of my own funding and I'm looking for 2/3 of my salary. But if you accept me both, you only have to pay me each for 1/3. And to my surprise, they both agreed right on the conference. So I didn't have to write a letter or something. So I came back from that conference and I was so happy. So I made my PhD and then we married, and like after 1 month after my PhD, I was married and we left for Stanford. And then I went to the electrical engineering department, so the information systems lab, ISL. And that's actually the first time where I met Stephen Boyd, because Stephen had then recently moved from Berkeley, where he had made his PhD, and he moved to Stanford. And he was already starting up his research on convex optimization and so on and so forth. And then, to be honest, I spent more time with computer science with Jean Golub for the very prosaic reason that there was more office space in computer science than in with Kailath, because Kailath had a lot of PhD students, a lot of postdocs. He was very well funded, but there was basically no office space. I mean, people had to share an office there. I mean, there were like 2 or 3 shifts a day where you could. So I was much more quiet in the computer science lab. I would say Kailath was a very agreeable but very serious scientist. He was very much involved also in all kinds of startup companies. He was very well funded, while Jean Golub was much more of a social figure. We got along very well. And Jean Golub also had a system of weekly seminars. So when you were in the computer science department, every week there was some big name that came and gave a nice presentation. I mean, these were really like world-renowned people that visited Jean Golub. And after that seminar, there was always dinner in a Chinese restaurant, I mean, where we shared all the food and so on. So Jean became a really good friend in such a way that he was traveling a lot. And so my wife and me, we were his favorite housekeepers. So I think of the 2 years we spent in Stanford, that about 9 months or so we lived in Jean Golub's house, because he was traveling a lot and we really got along very well. And that explains that the papers that I produced in Stanford are with Jean Golub, and I don't have any paper with Thomas Kailath, who, by the way, is still alive. He must be close to 90 now. We were supposed to celebrate his 85th birthday. I mean, before COVID erupted, we were supposed to celebrate Thomas Kailath's 85th birthday, but that never materialized because COVID came and it had to be cancelled and so on and so forth. And so once in a while, I still mail with Thomas Kailath, but he must be close to his 90s. And unfortunately, Jean Golub died like 15 years ago. So that was a kind of big loss for the community. When he died, we actually did something very nice worldwide, because Jean was this very sociable figure. So he had this big network of people that spent, I'm not talking about 10 people, I'm talking about hundreds of people that spent some time in Stanford with Jean Golub. So when he died on his birthday, which was the 29th of February. So it was a leap year day. 1 year after he died, we organized a world conference in the following sense, that it started in New Zealand and there was a handover to Australia, a handover to Beijing, a handover to Moscow, to Leuven, and so ultimately in Stanford. So that was a 24-hour conference where every 2 hours or so there was a handover via, Teams and so did not exist yet, but we had video connections. And so we did a 24-hour conference in honor of Gene Golub. And actually that was a very emotional moment for many of us because everybody really loved him. And he is of course very famous for having introduced the singular value decomposition, which we now use. It's probably one of the it's one of the most often used algorithms every day in the world, I think. But he was really the first person that, with some other peoples like Velvo Kahan and so on, wrote the first singular value decomposition code as we still use it today. So he was one of the first persons to do that, which, by the way, what nowadays seems almost trivial, that was not the case 40, 50 years ago, because these guys were really pioneers in numerical linear algebra, in numerical analysis, and so on. It's another manifestation. Some people say that automation is a hidden technology, but I think numerical analysis, what you use every day in Python, in Julia, and so on, and in all languages, is also another example of a hidden technology. It's just there, and we don't know how challenging it was to come up with floating point algorithms and so on and so forth. In the 60s, that was really a big challenge to come up with standards and protocols and coding mechanisms and so on and so forth. So these are giants, I think.
I fully agree. I actually had the opportunity to talk on this podcast with Liv Moller on a similar subject, the birth of MATLAB, and it was extremely fascinating to hear about their journey, into something that, is commonly used nowadays by literally everyone. But at the time, it was incredibly challenging.
Yeah. And for instance, I know several people that were there when the IEEE floating arithmetic, which is now the standard and so on. But, these things, they had to be conceived at a certain moment. So somebody had to do all the work. But that, I think my Stanford days are also very important for me for several reasons. So I worked with Kailath and with Gene Golub, but there were a lot of other PhDs and postdocs around. For instance, I learned a lot of Swedish people, Bo Wahlberg and Matt Viberg and Björn Otterstone, many, many others, because for one way or another, there was a very fruitful connection between Sweden and Stanford. So also Leonard Yu, of course, and then many, many other people. And so in the later phases of my career, I really was always happy that I could use my Stanford network. For instance, if you were looking for reviewers or for people that could be member of an assessment committee, the basis for that was really posed or led in Stanford in those days in Stanford. Another thing I learned there was it's in the middle of Silicon Valley. And that also triggered some entrepreneurship in me, because later on I created more than 10 spin-off companies. But the seed for that was made in Stanford, because I saw that, with your academic research, you can also create companies and you can attract investors and so on and so forth. So that's another thing I learned while being in Stanford.
I'm really, really curious about the subject. I'm personally interested in this as well, and I hope we can talk about it also later. I'm really looking for advice. I just want to mention one thing before we move on after the, let's say, Stanford years. Obviously, mention two of the papers that you wrote. So 3 of generalizations of the ordinary singular value decomposition, and then another one with Hongyuan Jia and Gene Golub, later with the restricted singular value decomposition properties and applications. 70 pages paper filled with lots of interesting mathematics. What I read also, I wanted to say, is that when you met with Tom Kailath, I think I heard it in an online presentation, he was opening with the sentence, "There are 168 hours in a week. What have you done this week?" Is that true?
Yeah, it's true, because, Kailath was a very, and I learned from him a lot, because he was a very well-organized person. So he had a very professional secretary called Barbara, And so he was extremely well organized, his funding. And one of the manifestations of his organizational skills was that he wanted to meet on a bi-weekly basis with his visitors, with his postdocs. So I was a research associate in Stanford. And then, because, these meetings, they lasted between half an hour and an hour, so they were very well timed. And one of the opening sentences he always said is, there are 168 hours in a week. Bart, what have you done this week? And that was a manifestation of the way he was thinking. I mean,
it feels a bit confronting to hear it.
Yeah, it's confronting. On the other hand, and in a certain sense, Jean Golub was the opposite, because he was always very relaxed and so on and so forth. But I think the truth is somewhere in between. I mean, on the one hand, you can lose a lot of time by chit-chatting and by talking socially to each other. On the other hand, you can also have really, I would say, return on investments when you use your time efficiently. Yeah? So that's, of course, you cannot exaggerate in neither direction. But I learned a little bit from both of them in how to deal with PhD students and how to deal with visitors. Actually, Kailath and Golub, they got along quite well. They knew each other. But if you ask me, they never did. There might have been some DARPA proposals in which they were both co-author, but if you ask me, they never collaborated intensively with each other. And by the way, in Stanford, I also saw a lot of other people. For instance, in the operations research department, I met Leuven, I met Danzig. I mean, all the famous people were there. At a certain moment, I met Solzhenitsyn, and I was not an engineer. Yeah, I met Schulz, I met Condoleezza Rice. So these were all people that were affiliated with Stanford. And you could, at a certain moment, I still remember that, last year there was the movie Oppenheimer. But I'm happy to say that, or maybe unhappy to say, that I met Teller, so the father of the hydrogen bomb, because he was a visitor in the Hoover Institute in Stanford. No, he was not a visitor, he was a fellow of the Hoover Institute, like Solzhenitsyn and so on. And Condoleezza Rice and Schulz, they were all affiliated with the Hoover Institute, which is a kind of right-wing think tank in Stanford. But on normal days, you could see these people walking on campus or eating their lunch in the Tresidder Union, which is a student restaurant in Stanford. And of course, I mean, I like that very much. You could see Nobel Prize winners and so on. You could go to all kinds of seminars. I mean, Stanford at that time was really a very busy and very interesting biotope. And of course, as a postdoc, you don't have any responsibility, so you can just attend to all these things without having any obligation, of course. I really learned a lot in my Stanford time. And of course, one of my closest friends is Stephen Boyd, so that's where I learned to know. And actually, one of my PhD students, later on, Leuven van den Berge, went to Stanford as a postdoc with Stephen Boyd. And there they wrote that very nice book, which is by now also a classic, on convex optimization. So that was really a joint work between Stephen and Leuven. Yeah.
I did see that connection. So Leuven had worked with you on building, as you were mentioning, resistors, nonlinear resistors in the style of Chua.
Well, the first connection was that I was the promoter, the advisor of Leuven's master's thesis. And the topic of his thesis was subspace identification. And he came with very nice results. But then he switched topics and he went to nonlinear systems. And he generalized what we did with piecewise linear resistive circuits. He generalized this to more general electrical circuits, so where you have also active components and so on and so forth. And so Leuven was basically publishing about complementarity problems and then the electrical circuit models that can be modeled with complementarity models, so to say. Yeah. So, but Leuven is for sure he is one of the brightest students we have ever had. So he's a very, very clever person. But he started his real academic career after his PhD with Stephen Boyd. That was a big step for him too.
So I'd like to shift gears now and move on to the next step of your career. I've seen that after spending these 2 years at Stanford, you moved back to Leuven, if I understand correctly, in 1990. And from then on, I see, I want to do a small captatio benevolentia to our audience and just mention that I will only be able to mention some of your PhD students, unfortunately, because of the sheer amount of work you've done. But just to say that I see very clearly that you follow different directions, and with specific PhD students, you essentially take some of these directions also in parallel sometimes. As you mentioned, with Peter Van Overske, you continue on the direction of subspace identification, but then also you branch off. For example, I'm thinking of Johan Saukens. I don't know whether I'm pronouncing it correctly.
That's correct, yeah.
On neural networks, where, as far as I understand, you were the co-promoter together with your promoter, Van der Walle.
Yeah.
So I'm wondering, how were those years for you?
Yeah, I think my promoter is also very instrumental in that, because Joost van der Walle was one of the first generation professors that we had who had spent 3 years in Berkeley. So, in the beginning of the 80s, that was still the time where about half of the professors in engineering, they had never done any research. I mean, they were clever guys and so on, but there was no tradition of intensive research and so on. I mean, they did some things, but not really. And then we had this first generation of professors that had spent time in Stanford or Berkeley or MIT, including Jan Willems, for instance. And they brought to Belgium the whole culture of that you have to do research to have an academic career and so on. Of course, there are always exceptions, but they installed a kind of new culture. And so I had a very good relation, or I have a very good relation with my promoter. I still see him quite a lot, although he has retired for 10 years now. But he was kind of visionary. And I think the common theme when you refer to the different branches that we started taking with our PhD students, I think a common thing to all of them is linear algebra. And so basically we were thinking in terms of linear algebra. When I say linear algebra, I especially mean numerical linear algebra. So using, Leonard Jung once said to me, because I was always referring to singular value decomposition and so on, basically, Bart, your program is to SVDize the world. And I said, yeah, you are right. I mean, but that's maybe but of course, that's a little bit of a joke, but it's more about linear algebra and the fact that you can do an awful amount of things if you have a proper knowledge in, let's say, advanced linear algebra. So we are not talking about the introductory courses, and I even learned that more with Jean Golub when we started generalizing all these singular value decompositions and so on. So these are new results in the linear algebra. And my opinion is that you can still get new results in linear algebra. Maybe we can come back to that later. But we started thinking about in how many different fields can we start using numerical linear algebra. And subspace identification was like a first thing. Of course, we did it. We invented it. The second thing was Johan Saukens, who started with neural nets, but pretty soon arrived at something that is called support vector machines, in which case you choose a kernel. So the art in support vector machines is choosing the right kernel, radial basis functions or Gaussian functions and so on and so forth. But once you have done that, you can basically translate any machine learning tasks in a question of linear algebra. So in a certain sense, the idea behind the support vector machine is that you project up your problem, which is difficult in a low number of dimensions. You beef it up to a high number of dimensions, an infinite number of dimensions via these kernels. But once you have done that, all that you have to do is solving sets of linear equations. You can SVDize certain problems. You can talk about canonical correlations. You can talk about principal angles. You can talk about eigenvalue decompositions. You can talk about dimensionality reduction, what have you. And so basically the idea is, again, linear algebra. There is a little trick, they call it the kernel trick, which is ubiquitous in machine learning. So you choose a kernel, but once you have chosen your kernel, all the rest is linear algebra. Of course, you have to work it out. And of course, it's also related to optimization because you have primal and dual formulations and so on. But many of the results in least square support vector machines or in support vector machines are just linear algebra. And so that convinced us that there is much more to linear algebra than you would think at first sight. So basically, you can make your career in linear algebra. But of course, you have to look for applications where you can deploy all the things you know in linear algebra in a very specific context. And so system identification, subspace identification is one of them. Everything that has to do with machine learning is another one. And later on, we did also other nice things. I had at a certain moment, I had 5 PhD students in quantum information theory. And this was, as I say in Latin, in tempore non suspectum, because there was even talk about quantum computing and so on. It's like 20 years ago. But I was convinced by one of my master students who walked in my office, and he said he was basically a very bad engineering student, but he was really into physics, theoretical physics, and especially quantum mechanics. And he walked in my office and he said, Professor De Moor, I don't know whether you realize that many problems in quantum mechanics are just linear algebra problems. And I was a bit surprised. Of course, I knew about theoretical physics. I've been reading a lot about that. And we spent an afternoon. And then because this was in the beginning of the 2000s, so I had quite some funding, because that was a lesson I learned from Kailath, that when you have a nice funding, you can once in a while start new directions in your research and so on. And so I said, okay, you convinced me, so let's go for a PhD. You can make a PhD with me on linear algebra and quantum information theory. And then this guy started working really hard. We managed to obtain several other grants. And after 2 or 3 years, we had 5 PhD students in quantum information theory. And for instance, one of the things we discovered there is that you can also come up with new types of singular value decompositions, which, when you do classical linear algebra, you work with Euclidean inner products. I mean, this is the usual inner product that we always use, but you can describe an inner product, define an inner product with respect to any metric, a positive definite metric, but also an indefinite metric. So an indefinite metric, for instance, in the special theory of relativity, it means that the inner product is characterized by the signature with 3 ones, 3 plus ones, and 1 minus 1. So the 3 plus ones corresponds to the space dimension, and the minus 1 corresponds to time. And so you have an indefinite inner product, which is kind of funny, because this means that a vector can be orthogonal to itself. And actually, in physics, it means that a light beam is something that is orthogonal to itself. I mean, it's kind of very, very disturbing to think about that. But nevertheless, the mathematics is completely sound. And so we described singular value decompositions in these indefinite inner products. And so this is an example where we started working in an area which we did not know a lot about, quantum information theory, but which also had some spin-outs in just linear algebra, because, we could publish double papers. On the one hand, the quantum mechanical interpretation, and on the other hand, the numerical linear algebra results, and so on and so forth. I stopped that research because I think nowadays it would be very hot, but 20 years ago we were too early. So nowadays, I mean, if you say, look, I have some PhD topics in quantum information theory, I mean, there would be a lot of people that would be interested. But at that time, after we had those couple of grants, it was a bit unclear in what direction it would all move. I mean, this was before the time that quantum computing was very hot, and so on and so forth. But to be honest, the 5 people that have made their PhD on that, all of them are now established professors in some universities in the world. And the first guy, Frank Verstraete, he is now in the physics department in Ghent, but he's really a big shot in the quantum computing world now. He has his second ERC grant now. He won the most famous scientific award you can get in Belgium. I mean, they call it the Belgian Nobel Prize, and so on and so forth. So he is really a big shot in that field. But he is still very thankful of me, because I granted him the opportunity in a topic which I did not know. But together we made it to a success, and basically it launched his career. So he is a very great name in that area now.
Just to do justice also to the paper, I believe the paper we're referring to is 4 qubits can be entangled in 9 different ways.
Exactly.
A paper that you published on Physical Review 8. I did note it down together with others around those years, Clifford group, stabilizer states, and linear quadratic operations over the Galois field too, of 2 elements. Again, on Physical Review, very fascinating subject. And as you say, it seems to be also quite popular these days in controls.
Exactly. Yeah, what Frank, for instance, is researching these days is it's also related to machine learning, because if you're working in these high-dimensional spaces like support vector machines, then we noticed that, of course, everybody says you're working in a high-dimensional space, but if you look at the manifolds where the useful activity happens in a neural network, these are always low-dimensional manifolds. And so, of course, in a quantum computer, you work also in an infinite dimensional space because a qubit can be a 0 or a 1 or everything between it. And if you have then 20 qubits, it's an exponential world that you're working in. But in a certain way, all the interesting activities also in a quantum computer happen on a low dimensional manifold. And this is very intriguing. And the ERC grant of Frank van Verstraeten is basically asking this question by exploiting the idea that the interesting things happen on a low dimensional manifold. Maybe we can have also a model of a quantum computer. Of course, we cannot really simulate a quantum computer, but maybe we can do useful things by exploiting the fact that it's basically working on a low dimensional manifold. And so there they use all kinds of ideas that also come from tensor algebra. And that happens to be one of, because you were saying several other PhD students started walking into different branches. And one of these branches is everything that has to do with tensors and high order SVDs. And that's basically the career of Leuven de Lathouwer. So he was my PhD student. And I gave him the problem, like we know about singular value decompositions for matrices. But what if you have a cube of numbers? Could you also define a singular value decomposition? And actually, he found nice results. It's not only one singular value decomposition. There are many different notions of singular value decompositions in more than 2 dimensions. But Leuven basically launched his career on what today is called tensor algebra. And if you, for instance, consult the SciAm journal called SciMax, so matrix applications, then it's, I think, half of the papers in SciMax these days is about tensors. So it's really a new branch, which is very exciting, which leads to blind identification and so on and so forth. And so that's also another thing that by starting from linear algebra, we can do many things. There's one quote I would like to cite here. One of those PhD students in quantum information theory, at the end, at his final presentation, he concluded by saying, look, quantum mechanics is notoriously difficult to interpret. And he said something like, I know it's very difficult, and I apologize with the jury members that I have this mixture of physics and of linear algebra. But in order to be correct, to kind of reassure you, he used the phrase that at the very end of the day, the only thing we really understand is linear algebra. And actually, it's a little bit true, because in those works, in those papers, I understood the linear algebra. But when they try to explain to me what it really means in terms of quantum mechanics, that's because, the very basis of quantum mechanics, even the biggest experts, they do not agree on how to interpret deep down there on how to interpret quantum mechanics. So
I did note down this citation that you have often at the end of your presentations. I find it very cute and funny. It's something that I wanted to mention at some point.
Yeah.
As you say, Leuven de Lathouwer is another PhD student of yours, publishes this paper, a multilinear singular value decomposition, together with you and Joost van der Walle. And also another paper, I'm just going to read the title, on the best rank 1 and rank R1 to Rn approximation of higher order tensors.
Mm-hmm.
So, and as you say there, you do address the question of how do we generalize the singular value decomposition to essentially arrays, multidimensional arrays of data rather than matrices.
Actually, that the title there that you read is very interesting, because For instance, if you work with a matrix, you can define the column rank of a matrix and the row rank of a matrix. And by some magic, for a matrix, they are the same. So if I give you a 10 by 7 matrix, the columns, they live in a 10-dimensional space and the rows live in a 7-dimensional space. But if you look at the rank of that matrix, for instance, the rank is 3, then it's a kind of very funny fact that in that 10-dimensional space, you have 3 linear independent vectors with 10 components. But simultaneously, in the 7-dimensional space, you also have 3 linear independent row vectors with a different number of components. They live in different spaces. And in a matrix, the column rank is the same as the row rank. And that property, which helps us a lot when doing linear algebra, that disappears when you go to higher dimensions because you have several notions of ranks in higher dimensions. And so, for instance, if you have a 3-dimensional tensor, you could still talk about rows and columns, and maybe in the 3rd dimension, you call it levels. But then the column rank and the row rank and the level rank, generically, they do not agree. And then the question is, of course, when you try to define a singular value decomposition, I mean, what are you trying to do? What does orthogonality mean in 3 dimensions? So, I mean, there are lots of basic questions that you have to think about when you're doing that type of algebra.
Indeed, I find it extremely fascinating, and I must confess that I did participate to one of these international schools in Leuven, offered by Leuven de la Tower on the subject, because I was really drawn to basically the tools that one uses and the fact that so many basic questions are, to the best of my knowledge, not answered. For example, even what is the correct notion of eigenvalue?
Yeah, sure. That's another one.
If there is one.
Yeah. And I think we refer to Frankfurt-Straten quantum information theory, we refer to Leuven, and there's now a new link between the two of them because in the research of Frankfurt-Straten in quantum information theory, basically they use a notion that they call tensor trains. And these tensor trains are very close to the tensor algebra that is being developed by Leuven. And so that's also a thing I'm really proud of, that my former PhD students, they still know each other, of course, but they discover new directions that they can go in with their PhD students. So, I mean, that's kind of fascinating to see how all of that develops over time.
I'm very curious how that unfolds as well. As far as I remember, tensor trains, just for our audience, are intelligent ways to factorize, essentially, tensors in order to mitigate the curse of dimensionality, basically.
Exactly. Tensor trains is a way of factorization, and at the same time, you do dimensionality reduction. I mean, that's basically the idea. And that relates to what I said, that lots of the activity in these high-dimensional spaces manifests itself on low-dimensional manifolds. I mean, these are all, let's say, all visualizations of the same idea. Yeah.
I have 2 more, let's say, linear algebra-inspired works or streams of work, if you wish, in mind that I'd like to mention because I found them particularly fascinating. One is the notion of principal angles between systems, if one thinks of systems as subspaces. And then obviously also the PhD thesis of Catherine de Kock, but also the work of Ivan Markovsky that I believe you supervised together with Jan Willems on exact and approximate modeling in the behavioral setting. Both of them I found particularly interesting also for our audience. Just the very idea of defining what is an angle between 2 systems is quite fascinating, and the connection also to the Martin metric. I'll mention that if for our audience, if they want to consult the dedicated article, it's Subspace Angles Between ARMA Models, as I mentioned with Catherine de Kock on systems and control letters in 2002. And in 2005, there is, as I said, this co-supervision with Jan Willems with Ivan Markovsky, where basically, I guess you build on the 3-part paper that we mentioned at the beginning of this episode, thinking deeply about the notion of most powerful unfalsified model, which we haven't mentioned yet, and also how to deal with different classes of systems potentially.
I think I will come back later on on the work of Ivan Markovsky, but you are right. It's a kind of further development on the behavioral papers of Jan Willems. And Ivan did his PhD with us in Leuven, but then he moved to the University of Brussels. And I think he moved now to Spain, but I don't remember. I think it's somewhere in Catalonia, but if it's Barcelona or another university, I don't remember. But indeed, and we have also written a book about that with Jan Willems, myself, and Ivan, and Sabine van Huffel, who was a fourth co-author. And that's basically working out the idea about misfit. And actually, it's also a source of inspiration for my current ERC grant, which is also about trying to formalize the idea of misfit. But I guess we can come back to that because that's the last phase of my research career so far. The Katrien's thesis is very interesting, I think, because there, what I also like in my research is that it plays, everybody these days is talking about interdisciplinarity and multidisciplinarity and cross-disciplinarity. But Katrien's thesis is a very nice example of that because it kind of unifies notions that come from information theory. So Shannon entropy on the one hand, subspace identification on the other hand. We talked about Akaike. And the third angle is statistics. And so when you read Katrien's thesis, and by the way, you can download all the PhD theses we are referring to from our website somewhere, so it's not difficult to find them. But what Katrien basically did is that if you have a linear stochastic system, so this is a linear time invariant system, a state space model, but there are no deterministic inputs. There are only stochastic white noise inputs. And at the output, you get colored noise. And that's basically the setting that we are talking about here. And then I explained you that in subspace identification, if you read Akaike's original paper, then basically you can identify the state sequence of such a system by looking at what is called principal angles and directions between some past and future Hankel matrix. So you have output only data because it's a stochastic system, so you have only output data. What I'm saying in principle only applies asymptotically because in principle you need infinitely large matrices, but you can approximate it very well with large data sets already. And basically, when you make such a past and a future Hankel matrix with the output data, you have most of the directions in the row spaces of those Hankel matrices will be perpendicular to each other. But a finite number of them, namely a number equal to the number of states, will not be perpendicular. Said in other words, there will be non-orthogonal angles between those directions. And what are those directions? Well, you know what an angle between two vectors is. You can calculate an angle, the cosine of an angle, with some inner products and some norms. I mean, it's the theorem of Cauchy-Schwarz, basically, where you can calculate the cosine of an angle between two vectors. Well, that notion can be generalized to several angles between subspaces. And so we call them principal angles and directions. And it should come as no surprise when I tell you that you can calculate these things using a singular value decomposition. That was one of the things I learned from Jean Golub. So he has a nice paper about principal angles and direction with a Swedish researcher called Åke Björk, who is still alive, by the way, but he must also be very old. And you can calculate those angles and directions using a singular value decomposition. So that's one part of the story. And Akaike was talking in statistics, they call it canonical correlations, but in numerical linear algebra, they call it principal angles. By the way, the notion is definitely not new. In statistics, it was discovered by Hotelling, but 100 years before that, the first paper on angles between subspaces is by Jordan. And I have to be a bit careful now because there are several Jordans, so I don't know whether this is the same Jordan as the Jordan canonical form or the Jordan curves and so on and so forth. There are several Jordans, so you have to be a little bit careful. I don't remember right now. But it's Jordan who first, and who said that calculating the angles is basically an eigenvalue problem, but it's a symmetric eigenvalue problem, so you can do it with a singular value decomposition. The second thing is that we could then link this up, these angles, if you make products of the cosines of these angles, that happens to be an information measure that really describes, that characterizes a distance between stochastic systems. So in a certain way, if you have an ARMA model, stochastic system 1, and you have a stochastic system 2, you can describe a distance measure between two such systems by using these notions of angles, because the product of these angles is exactly the Shannon information property. And I'm not going to elaborate on that because that requires some formulas. You can find all of them in Katrien's thesis. But that I found a very intriguing idea, because if you can give me a distance measure between systems, or if you think about behaviors between data generated by these systems, I mean, these notions are equivalent, then of course, when you can start clustering time series, because if you have time series and each of them is being generated by some ARMA model, you can ask yourself, how many different types of time series are in my batch, are in my database? And basically, you can use your favorite clustering algorithm. And for a clustering algorithm, you need 3 ingredients. You need to define what a cluster is. You need a distance measure, because you want to calculate the distance of one time series to a certain cluster, or you want to define a new cluster. And you need to make a decision. You need a decision mechanism. Is it close to that cluster, or is it close to another cluster, and so on and so forth. So you need 3 ingredients for clustering. And so discovering this distance measure between time series, although it's a very limited class of time series, linear stochastic systems, but that opened a lot of perspectives, because it means that when you do machine learning, you can start thinking, how do we have to conceptualize clustering time series? And clustering time series, in my eyes, is a very challenging, still open problem. What I see in the big data science conferences is that many people that go there, they really don't know what a time series is. We know in this podcast, all the people that listen to this podcast know what a time series is. But a time series means, of course, that there is a temporal correlation between the samples over time. What I see in many machine learning conferences is that they treat a time series, they just put it in a vector of data, and then they use a classical distance measure between vectors to describe the distance between those two vectors. But of course, when you do that, you ignore the temporal correlation within that vector. So you can only talk about a good distance measure between time series if in one way or another that takes into account the temporal correlation in that time series. And that is exactly what Katrien did for ARMA systems. The nice thing when you work with ARMA systems is that you can obtain lots of nice mathematics. If you do this for more general time series, let alone completely nonlinear time series, then it's much more difficult, of course. But for ARMA systems, we could find very nice mathematics that relates Shannon information theory to statistics, to Akaike, to subspace, and so on. So maybe the domain of applicability is limited because we are talking about ARMA time series. But on the other hand, the mathematics that came out of it is really very nice. I mean, it relates results from several disciplines. And that's also, when you're doing research or PhD research, I think it's also sometimes rather fruitful to focus on maybe a limited problem and arrive at a lot of nice results, rather than trying to cope with a very general problem formulation and then end up with a lot of heuristics. I mean, there is something you can say in favor of both of them. But what Katrien did was this rather focused problem, but she could arrive at a lot of interesting results. So relating angles and information theory and so on and so forth, and clustering. So that was a very nice thing. And by the way, Katrien, she spent quite some years abroad. She was in the States and she was in England. But like 5 years ago, right when I was going to write my ERC grant, she came back to Belgium, and she is still today my right-hand researcher. So we are writing a book together, and I'm very happy with Katrien on my side in this ERC grant.
Just one comment on the subject of subspace angles, and then I think we have to move on in the interest of time. I found in one of your presentations, perhaps online, or maybe I participated in person, very telling this example of relating a sine and a cosine, thinking of them as orthogonal, as time series, but also thinking of them in terms of these angles. I thought it was very fascinating.
Yeah, that's actually a very good didactical example to illustrate what I meant when I said that many data scientists do not know about this temporal correlation. We as electrical engineers or as system theory people, we all agree that a sine and a cosine is exactly the same signal. The only difference between them is a phase shift. So you have a different phase. Now, suppose we agree on time zero, so we agree, and we put a sine in vector A and a cosine in vector B. And we do that for a sufficiently long time. Long enough. And then we start looking at the angle between those two vectors. And of course, for a sufficiently long time, when you calculate the angle, those two vectors will be exactly orthogonal to each other. So when you make the inner product of the elements of the components of those vectors, for long enough, it will be zero. So this means that the cosine is pi over 2 or 90 degrees. They are orthogonal. And if you think statistically, when a correlation is zero, then you tend to say there is no relation, no linear relation between the two. And of course, it shows that it's false because a cosine and a sine, the only difference they can have is the frequency, but when they have the same frequency, they are the same signals. And so when you come up with a clustering algorithm, if I give you a cosine and a sine, the clustering algorithm should assign them to the same cluster. And so this very nicely didactically illustrates that the correlation measure or the distance measure should be adequate for the task at hand. And you give a perfectly nice example where many clustering algorithms will fail because they use the wrong measure to measure correlation and to measure this type of temporal correlation. The temporal correlation in a cosine is exactly the same as the temporal correlation in a sine. So you cannot distinguish between the two of them.
Okay, so now I would really like to shift gears again because I would like to talk about one of your last ERCs. Well, your last ERC. It's called Back to the Roots. I find it particularly interesting, at least to me. I feel that this will be not necessarily fair to the other body of work that you've done on bioinformatics, also on traffic, that I find particularly interesting. But I think it's worth spending some time on this new stream of research. I'd like to hear from you what motivated and what it's all about.
And the motivation is basically what you said. So we have mainly talked in this podcast, we have been talking about linear algebra and all the things we have been doing with that. And of course, that's my first love. So I really like linear algebra a lot. But in the meantime, in my career, I've been doing many other things because we have done a lot of work in machine learning and in all kinds of other application areas, control, process industry, bioinformatics. About half of my current PhD students are in biomedical signal processing and bioinformatics. So we're talking about genomics and about proteomics and multimodality data sources and so on and so forth. But let's not talk about that. But at a certain moment, I thought to myself that in machine learning, many of the things are very heuristic. Because if you think about deep learning, basically what I do a lot of reviews of proposals and committees and so on. And basically the story is in many cases the same. You come up with a new architecture for some deep learning neural network. You choose your favorite optimization algorithm. There's a lot of pepper and salt on how to do that. And then you deploy your architecture and your optimization algorithm to some application. Bioinformatics and so on and so forth. And so many of these proposals look the same, and that's fine for me. But what has always been striking me is that there's a lot of heuristics involved in machine learning. And I'm not saying that it's not productive, because nobody will doubt that things like ChatGPT and generative AI and so on, they have a bright future. You can open the debate whether it's still science. Is it not just engineering? And if you want an analogy, I mean, people could already design first cars and motors without having an understanding of thermodynamics. And so basically, I think the same happens in AI. We know very little about, I mean, if you think about explainable AI and so on, it's all this type of questions. Why do we get the results that we get? And of course, it's heavily biased because only the positive results are published, and the number of publications where some negative results are published are very, very few. So the whole literature is very biased. And so at a certain moment, I started thinking, what is going on? And I thought, look, what is the class of mathematics or models that you need in order to still be able to say mathematical things in machine learning or in classification or whatever? And I thought at a certain moment that multivariate polynomials is a very rich category of things you can deal with. And back to the roots of my proposal, the roots in there have three different meanings. The roots refer to, at the first place, to eigenvalues. One of my favorite topics is eigenvalues and singular values and so on. And so let me explain. At a certain moment, I found that when you try to solve a set of multivariate polynomial equations, so basically that means that you try to find the common roots of multivariate polynomials, that deep down there, and that's a non-trivial result, that deep down there, it's an eigenvalue problem. The result is by no means original, but it seems to be forgotten, especially in the system theory community and so on. Of course, in a mathematical discipline called algebraic geometry, they know, but that discipline has evolved in a very abstract discipline, because I invite you to try to read something about algebraic geometry. They definitely do not use the language of numerical linear algebra. It's very abstract. I mean, because they are not dealing with the field of complex numbers, they deal with rings and they deal with modules and so on. I mean, it's a level of abstraction that is very important, but that is very hard to understand. And so I started thinking about how can you find the roots, the common roots of a set of multivariate polynomials. And then I realized that when you go back 150 years and you try to understand what Sylvester did, then basically he had an elimination theory, like Gaussian elimination, but he had it for multivariate polynomials. So this means that you can, with some tricks, you can eliminate a certain, suppose you have a set of multivariate polynomials with 10 variables and you have 10 equations, you can eliminate one of the 10 variables by taking linear combinations of the equations and so on and so forth. I'm not going to go into the technicalities, but you can eliminate one variable out of those 10 equations. And then you have 9 variables left. And then one by one, you can eliminate them. And at the very end, you end up with a big polynomial in one variable. And of course, we know that when you are interested in the roots of one polynomial in one variable, that's equivalent with an eigenvalue problem. And so maybe Sylvester did not call it like that, but that's the result he obtained. So he had an elimination theory, and maybe you have heard about resultants and so on. So that was the technology he used, resultants, which are basically determinants in a certain way. And so he has an elimination theory by which he can eliminate all variables except one. And at the end, you end up with a univariate polynomial that you can root. I mean, you can root it using there you have Galois theory and so on. And if the order is higher than 4, there are no analytic formulas and so on and so forth. But it's an eigenvalue problem. I would like to paraphrase Stephen Boyd here, who says that when you can reformulate a problem as a convex optimization problem, it's solved. Of course, we all know that's not completely true, but we all know what Stephen Boyd wants to say. I mean, you feel comfortable because it's convex. Well, I have a kind of same phrase when I recognize that something is an eigenvalue problem or a singular value decomposition problem, I consider it solved. Of course, what I'm not saying is that this elimination theory of Sylvester leads to very large eigenvalue problems. I mean, it's large-scale eigenvalue decomposition that you need. But you have to know that these days, with the current state of numerical linear algebra, we can solve eigenvalue problems that go in the millions, because the matrices that we use are very sparse, they are very structured. And if you look, for instance, at weather models, they solve eigenvalue problems 1 million by 1 million, 10 million by 10 million, using iterative algorithms and so on. So there's a complete state of the art on how to deal with large-scale eigenvalue problems. So that's one ingredient. And now you might ask yourself, why was I interested in multivariate polynomials? Well, if you take a typical system identification problem, and let's confine ourselves to linear systems. Take Leuven, prediction error methods. Basically what you have, let's take single input, single output. Let's keep it simple. You have a linear system, you have a difference equation, you have unknown parameters in there, and you have also unknown noise variables in there. And the noise variables interact with the parameters because you have products between noise variables and parameters. So this is a kind of multivariate polynomial-like thing. You have unknowns that appear in your problem as products. So if you have an ARMA model, for instance, you don't know the state space model and you don't know the noise, the driving noise inputs. So you have a product between the inputs and the unknown parameters of the model. And then on top of that, you formulate an optimization problem. Typically, it's least squares. And least squares is also a sum of squares. So it's multivariate polynomial. So when I have a prediction error method, I have an objective function that is least squares. I have constraints, which is my model, and these are multivariate polynomials. When you then use Lagrange multipliers and so on, you end up with a set of multivariate polynomials of which you want to obtain the roots. So that's directly the connection between this set of multivariate polynomials and system identification. If you want to have an easier example, you refer to Markovsky and we refer to Kalman and so on. Take realization theory. If the impulse response samples are exact, you can exactly solve the realization problem. So you can go from an impulse response to a state space model. And that requires a singular value decomposition. But what do you do when the impulse response samples are not exact? This means that the Hankel matrix will not be rank deficient. Well, you can reformulate that problem in a behavioral way, so using misfit and so on, least squares. So basically the question you are asking yourself is, how can I change the observed impulse response samples, which are not model compliant? I mean, the Hankel matrix is in no way it's rank deficient. So how can I change them, the data, in a minimal way so that the modified data are model compliant, so that when you throw them in a Hankel matrix, that Hankel matrix is rank deficient. And that's the definition of model compliancy in this case. And so when you write out the equations for that optimization problem, you end up with that you have to find the common roots of a set of multivariate polynomials. Said in other words, every misfit problem with linear systems, deep down there is an eigenvalue problem. So when I paraphrase Boyd, it's solved. And so I'm saying that noisy realization, as you could call it, you can solve it exactly, but it's an eigenvalue. It's a large-scale eigenvalue problem. We say something more. We can, because these nonlinear optimization problems have a lot of local minima and maxima, but we can even calculate the global minimum. So that's something we share with convex optimization. We are guaranteed to find the global minimum. We can also find all the other local minima, but one of them is for sure the global minimum. So what I'm saying is that in one way or another, the global minimum of such a least squares prediction error method is an eigenvalue of some large matrix. I mean, that's basically what I'm saying. And so said in other words, all the heuristics that Leonard Leuven is trying to do in his prediction error methods and in his toolbox in MATLAB is some heuristic way. Leonard hates that when I say that. It's some heuristic way to try to solve a large-scale eigenvalue problem. I mean, he has never phrased it in that way, but that's the statement that I'm making. It's an eigenvalue problem. And so you have a lot of parameter estimation problems and system identification problems that are multivariate polynomial. And so when you write down the first order optimality conditions, you end up with a set of multivariate polynomials of which you have to find the common roots, and even better, in which you have to find the one minimizing root, the one that represents the minimum, the global minimum of the whole problem. So that's basically the basic idea of my ERC proposal. And that's the first meaning of the word root. It refers to this kind of eigenvalue statement. The second meaning is easier because that refers, it's a kind of melancholic statement, because I have been doing for 30 years, I've been doing many things, not only in science, but I also had some management responsibilities and also in politics and so on, but that's another podcast. But basically, it's a melancholic statement because when I was thinking about this 5 years ago, and of course with the appearance of ERC grants, because that's a relatively new funding system in Europe, I said, why would I not go at the end of my career for an ERC grant? And actually I did that because I was still a little bit melancholic about the start of my career in Stanford and so on, where you could devote your whole day on doing research, of course. And when you have this academic career, and so you have to do many other things. And so back to the roots refers to the beginning years of my research career, and actually also to my PhD. We started with my PhD, in which there were still a lot of unsolved problems. So in a certain way, I take up these unsolved problems and I try to solve them now as eigenvalue problems. And the third meaning of roots, and we have talked about that also, refers to my mentors. So my promoter, Joost van der Wallen, but also people like Kalman or Kailath or Jean Golub and so on. And Jan Willems. And in my proposal, I even, I explained in a couple of paragraphs, I explained the meaning of the title. And so that was in a scientific proposal, but I like to do that in a certain way. The proposal and the results also pay tribute to my mentors. So that's a threefold meaning of back to the roots. I'm really happy with that proposal because it's really fundamental research. When I informed Leuven van den Berge that I obtained this proposal, he was a bit jealous because he said, in the States, we don't have such big grants that are only for fundamental research, because this is in a certain way. Of course, I have applications in mind, but at the first place, it's kind of fundamental research proposal, and that's the way it's written too. And so I'm really happy. And at this moment, I have about 7 PhD students that are working on sub-problems that are related to this proposal. And so, this back to the roots is really a very nice thing. I also said in my proposal that I'm not going to write 500 publications about this, because I have enough publications. I don't have to do it for that. But that we are going to write a couple of books about it. So that's basically the output we are going for. And then therefore, Katrien is very instrumental to help me out, because, writing a book is not nothing. So that's basically the output that we expect from this proposal. So to summarize, it's a mixture of system theory, because there's a lot of system theory in the proposal. Also, we again arrive at a lot of new linear algebra results. You might have heard about the Weierstrass canonical form, which is the generalized eigenvalue decomposition. But now, just like we generalize the singular value decomposition to any number of matrices, we can generalize the Weierstrass canonical form, which is an eigenvalue problem, to any number of matrices. And these matrices, we can link them up to multidimensional state space models. So we really describe the dynamics of what is going on in trying to solve this set of multivariate polynomials in order to explain some of the mechanisms that we see in that theory. We use multidimensional systems theory. And so in which case you can also talk about multidimensional realization theory and so on and so forth. So it's another manifestation of the fact that linear algebra is really inspiring for a lot of new things. When I talk to people from algebraic geometry, like Bert Stumpfels and so on, who's one of the big shots in algebraic geometry, even for them, this relation with numerical linear algebra, this relation with multidimensional system theory and so on, is completely new for them. So that's another message I want to convey. It's not because there is a discipline like algebraic geometry that you should, that you can also contribute from other disciplines to, in this case, the discipline of algebraic geometry. There's very little literature about the numerical aspects of algebraic geometry. It's very abstract, and they use a lot of symbolic calculations and so on, but they don't use numerical linear algebra. And so that's one of the things we try to contribute to that. It's basically new research, I think. Yeah.
I think this line of research is extremely fascinating and deeply original. I'm familiar with much of the mathematics that you mentioned until now. For example, finding least common multiples and greatest divisors, the Euclidean algorithm in more general structures, let's say. And I find it very, very fascinating. And the use of Macaulay matrices, the use of ND, so-called realization theory, to solve these problems is somehow miraculous in a sense that you can get the globally optimal solutions.
It's a nice example you gave, because in algebraic geometry, one of the big notions there is things like a Grübner basis. But a Grübner basis, that's based on a kind of generalization of the Euclidean algorithm and so on. And that, for instance, you can imagine that you work with integers only. Then you're working in a ring, you're not working in a field. And basically what we do is we say, look, of course, it's very powerful that you can work in rings, but when we work in engineering, typically we work in the field of complex numbers and real numbers and so on. And therefore, all the things you can do with Grübner basis, you can do better with classical numerical linear algebra algorithms, like determining ranks and determining eigenvalues and so on and so forth. And this, in a certain sense, to them is new, because they did not realize that when you kind of relax the structure of the number fields you're working in, that you can use much more numerical linear. You can use numerical linear algebra as a tool, which you cannot do when you're working in a ring of integers, for instance. So it's a different way of thinking. It's complementary. Yes. So that's what is fascinating. And it's an eigenvalue problem. That's the most important statement, I think. Yeah.
I'm going to mention for our audience, sorry to jump in, that if they want to start and look into this stream of research, there's a couple of PhD theses that I see originating already in 2013 by Philippe Drezen and Kim Botzelier. And also something a bit more recent, 2019, least squares realization of LTI models is an eigenvalue problem. This somewhat provocative title, the European Control Conference, a single author by you. Extremely fascinating subject. I'm looking forward to see how Macaulay matrices become a bit more popular in our field.
Yeah.
So since we are left with about 10 minutes in the recording of this episode, I'd like to dedicate ideally the last 10 minutes to two subjects that I find particularly interesting. One is entrepreneurship, and the other one would be advice to future students. So you've been launching about, certainly more than 10 companies based on the research you've done. I guess the question I have is suppose you're a student today and you have an idea that you think has commercial value. What should the student do in terms of, say, intellectual property, funding, legal aspects? What is the advice that you can give based on your experience?
I think the way I started being entrepreneurial is I talked about Stanford, and the first spin-off we created was a bit lucky. We had a piece of luck there. That was with Peter van Overschie, because we mentioned the book on subspace identification, and the last word in the title is implementation. And in the book, that meant that when you bought the book, there was a floppy disk with all the MATLAB files, and because this was before the internet and so on. So there was a floppy disk. And at a certain moment, I get this phone call from the headquarters of Shell in Rotterdam. And there was a guy that said, look, we have been using your software for a couple of weeks now on trying to model oil drilling. So they have these old oil drilling installations. And he said, it works like dynamite, but we don't understand anything about the theory. So we went there, and it was a very nice meeting. And then they offered us, basically, to cut a long story short, a contract. And that created our first spin-off company. And Peter van Overschie and one of his PhD colleagues, Christian Moon, started the company. It is still there. It's called ep26. But they sold it 1 year ago. So they have been doing oil drilling and process control based on subspace algorithms and so on and so forth. And so we were lucky there. But then once I got a taste of it, I started looking around how can they. And one advice is, if I look at my own career, once you have the reputation of being entrepreneurial, you attract a special profile of PhD students. I mean, you attract the classical PhD student that just want to do maybe some engineering research or theoretical research, but you also attract a profile of people that want to be entrepreneurial and that are looking for a topic by which they can commercialize later on. So that's one thing. That's a bit of a disappointment that I have now also, because when I look around in my own university and as an entrepreneurial university, we are very good because we are number 8 in the world when it comes to innovation and entrepreneurship and intellectual property and so on. So the 7 first are American universities. I think ETH is closed, but it's behind us, Alberto, in that ranking. Of course, you have a lot of rankings. So I do cherry picking in the rankings.
Depends on the ranking.
Exactly. I do cherry picking in the ranking now. But in any case, so you attract a special type of PhD student. When I look around, I see it's a little bit of a disappointment, because in the 90s, I thought that all my colleagues who were making their career with me would be entrepreneurial, but that's not true. So most of the professors still are not entrepreneurial at all. So maybe at first advice is that you have to talk to your promoter beforehand, whether he is willing to guide you in, not from day one, because first you have to obtain your PhD, but you can already start looking around for opportunities while you are making your PhD. And that, of course, requires maybe some special attention of your promoter. He or she should be sensitive to that, should accommodate your desires in that respect. The second thing is that you have to think, in my eyes, of the 10 spin-off companies I created, technology, basically all we do is machine learning or modeling. I mean, it's always data-driven. We don't do other technology. We do the models, the mathematics, and so on. But you have to look for a nice focused market. And if I look at my spin-offs, about half of them is in the process industry. There we are talking about process monitoring and data science applied to process industry, chemical industry typically. And the other half is in bioinformatics. But even there, you have to try to find out the return on investment. And what I mean by that is that if you sell a product or if you sell a service, you have to try to find out what, at the end of the day, when a customer buys your product or your service, what is the return on investment for him when they buy your product? And this is very important, because it means that the same piece of software, that you can sell it for a completely different price, depending on what your customer is going to earn with it. For instance, in the chemical industry, they are prepared to invest an amount of money when they can gain back that amount of money in 1 year. So when you sell them some control tool or some model predictive control or what have you, typically they are not concerned with how you do it and so on, because in many cases they don't understand. But if you can promise them that when they do an investment and they can gain back that investment in 1 year, that's the price they are willing to pay. So if you sell something MPC, for instance, in order to decrease the energy consumption and to be compliant with all the CO2 emissions and so on, you can find out what amount of money that means for your customer. And so if they earn like 5 million euro with that, you can then calculate how much money you can ask for your product. And that's a little trick, that the return on investment period in every discipline, in every industrial field is different. It's different in the medical field, it's different in the... So you have to find out that kind of marketing mechanism, that kind of payback time, and that allows you to include a certain pricing in your business model. So in my opinion, the problem is never in the technology, because we are trained as engineers. We are very flexible. When we have an unexpected complication, we always find a technical solution to solve it, especially when you are in data science. But the business plan is basically in who can earn money with what you are selling and over which period of time. And this really means, and that's sometimes very difficult for engineers to accept, that in one sector you can sell a piece of software for, let's say, €1,000 or €100,000. But in another sector, you can sell exactly the same piece of software, but maybe for €500,000. And engineers, they are rational people. They say, well, yeah, but that kind of bullshitting the world. But that's not the case. I mean, because in that other sector, they earn other amounts of money with your software, maybe on a shorter term. I mean, there are quite some parameters in there. And I think before you start a business, you have to find out what the mechanisms are on how you are going to sell, for what, to whom, and for what price. And actually, this information is also very important when you go to an investor, because your investor will also not understand anything about the technology, but he will understand what the market is that you are going to go for. And another problem that many engineers and data scientists make is that they consider neural networks or deep learning, they consider it to be some kind of universal solution to anything, but that's not how the market works. I mean, you cannot sell things in the medical sector and at the same time sell the same thing in the chemical sector. I mean, these are two different markets. And so you really have to think about in what market you are going to sell something, because if you try to pitch that you have been successful in the chemical sector, and then you go with that pitch to the bioinformatics sector, they will not understand what you're talking about. So it's very important to speak the language of your customer, and they will not be impressed by other successes. We started the podcast with soccer. When you have been a successful swimmer and you go to play with a soccer team, it will not help that you tell them that you're a successful swimmer, right? I mean, are you a good soccer player? And it's the same in trying to set up a spin-off company. So you really have to think in terms of what are you going to sell and for what price and to whom, and what will for them be the return on investment. And in many cases, that's not an easy exercise. In many cases, that's a complicated exercise. Yeah.
So in summary, talk to your promoter, find your own niche market, and speak the language of the market that you're targeting.
And talk to people. In my case, the more spin-offs I created, the easier it became, because you have also the people that have already done it. And so in the last couple of spin-offs that I founded, some of the first successes, I mean, the CEOs of the first spin-off companies are created, are now investors in the latest spin-offs. And they are experienced, so sometimes they become chairman of the board, and then you have a lot of experience on board. So also try to work on your network. It can be former PhD students of your university or of your promoter. I mean, try to build up your network, because the social aspect and having the right type of information is very important in setting up a business. Yeah.
Well, Bart, I am aware that unfortunately our time is limited, and so we're coming to the end of this episode. Thank you so much for joining us.
Thank you very much, Alberto. Enjoyed the talk.
Thank you for listening. I hope you liked the show today. If you enjoyed the podcast, please consider giving us 5 stars on Apple Podcasts, follow us on Spotify, support on Patreon or PayPal, and connect with us on social media platforms. See you next time.